Okay, so 5, 9 is complex numbers. And up to this point, like I just said, we haven't been able to take the square roots of negative numbers. So today we're going to talk about how are we going to do that. So we're actually going to be able to take square roots of negative numbers. So imaginary numbers are square roots of negative numbers, real numbers. Where I squared is equal to a negative 1. Meaning, if I were going to take the square root of I squared, then I would be the square root of negative 1. Do you see that? So for any positive real number, b, if I have the square root of negative b squared, remember I can pull that guy apart. We had a rule at the very beginning that said I could do them individually. So I could say that's b squared, and we could do that, times the square root of negative 1, and we just defined the square root of negative 1 as I, so that guy would be b times I. So essentially, anytime we have a negative under a square root, he comes out as an I, or an imaginary number. Okay? All right, so number 1 here says simplify each expression. So this is the square root of negative 28. Let's think about that guy, and instead is the square root of negative 1 times the square root of 28. Well, we defined the square root of negative 1 as I, so I'm going to change that guy to I. And what about the square root of 28? How have we been doing those guys up to this point? Yeah, we factor tree it, right? We make up prime factorization, so we're not changing that part of it. 28, let's do 4 and 7, and 2 and 2. So I can get a group of 2's to come out. And I ran out of room. So this guy is I times 2 root 7. And the actual correct way to write it is the number first. So that guy would be 2I square root of 7. So the negative comes out as an I, and then it's what you've been doing.
If the number is imaginary, how, when are we going to?
Good question. Remember when we were factoring and we had those ones that were the difference of squares? And I said, wait, we can't factor it if it's the sum of squares. In order to actually solve that, we need imaginary numbers. And we'll get there by the end of our notes. So I'll show you. Or actually here, number 3, I'll show you. Okay, so look at letter B there. I have a negative under a square root. So the first thing I'm going to do is take out an I. Okay, so this guy is really I times the square root of 32y cubed. And then I'm going to do that 32y cubed just like we've been doing the whole time. So factor tree it and see what comes out. Let's do 4 and 8, and 4 and 2. We got another 4 to come. Y. 2 will come out. Okay, so what gets to come out? A 4 and a y. So I have 4y I. Who's left? 2y. Perfect. Now i's behave like variables. So if you look at letter C there, it says negative 3i times 2i. Well, negative 3 times 2 would be a negative 6. I times I is I squared. So that guy's negative 6i squared. But we figured out up here, they told us that I squared is negative 1. So I'm going to replace that guy with negative 1. So negative 6 times a negative 1 gives me positive 6. I can't leave an exponent on an I in my answer.
Oh, because it's in negative 1.
Yeah.
In the radical, and if you multiply it by another negative 1 in the radical, then it's just negative.
Perfect. Good job. Okay, look at letter D. Letter D says the square root of negative 12 times the square root of negative 2. Now, the trick with these ones is you have to take the i's out first. And you say, but I can't see. I took my eyes out. Ha ha ha. Bad math jokes. Okay, so take the i's out first. So the square root of negative 12 becomes I root 12. And the square root of negative 2 becomes I root 2. So if I multiply those two guys together, what do you get? I times I is I squared. And 12 times 2 is 24. And then let's fix that guy. Let's factor 324. We just did 12 and 2. And 2 and 6. And 2 and 3. So a group of 2's get to come out. So this guy is I squared times 2 root, 2 times 3 is 6. And we remember I squared is negative 1, so I'm going to change that guy to negative 2 square root of 6. Okay, questions so far?
When you said imaginary numbers, that's what we thought my math really so, and that makes sense.
It's not bad at the moment, right?
At the moment.
At the moment. It actually doesn't get bad. I know there's the concept that it does, but this one doesn't. Okay, so there's this box here. You have to know this box. Okay, so as I just said a moment ago, we can't leave an answer that has an exponent on an I. So anytime we have an exponent on an I, we have to fix it. Okay, so here we go. This box says I to the first. Well, that guy's just I. Technically, it's also the square root of negative 1, but in our answers, we can leave I as just I. Okay, what was I squared? Negative 1. Okay, I to the third power. Well, let's investigate I to the third. I to the third, I could also write it as I squared times I to the first. Would you agree with that? Okay, so that being said, we know I squared is negative 1, and I we can write as I, so I to the third power is negative I. Mind blown a little bit. Okay. Okay, so let's look at I to the 4th then. How could we write I to the 4th? There's lots of ways. Just pick, yeah, how could you rewrite it? So like, we could do I squared times I squared. Or we could do I to the 3rd times I. Does that make sense? So we're just trying to rewrite it in terms of ones that we know.
So if I squared times I squared, so it would be -1 times -1, so it would just be 1.
Perfect. Now it says it repeats every 4 powers of I. Okay, let's check it just to make sure it works, because that's saying that this should be I to the 5th, and then I to the 6th, and I to the 7th, and I to the 8th. That's what that means, right? So let's check I to the 5th, just to make sure. So how could I rewrite I to the 5th?
I squared times I squared times I inverse.
Okay, that's one way, yep. So I squared times I squared is -1 times -1, and I is just I. So that would be -1 times -1 is a +1 times I, so just I. Hey, look, that's what it said. Okay, so it repeats every 4 powers of I. So it would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? And I told you that your answer, you couldn't leave an exponent on an I. Okay, so now look at number 2 there, 35. I to the 35th. Do you want to sit there and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, till 35? That'd kind of suck, right? Matt? Yeah, we're trying to find the next smallest number divisible by 4, right? So what he's saying is, okay, that would be 4, and then 8, and 12, and 16, right? So we're actually trying to find the next smallest number divisible by 4. So let's count backwards. Is 34 divisible by 4?
No.
Is 33 divisible by 4?
No.
Is 32 divisible by 4?
Yes.
Yes. Well, how many times did we go backwards?
8. Wait. No.
3, right? It was 32, right? 32? Oh, I shouldn't do that for the class. You guys at home, I'm sorry. 32, 33, 34, 35. So this guy is the same thing as I to the 3rd. Because 36 is also divisible by 4 too, right? So this guy would be 36, 35, 34, 33, 32. Okay, and what's I to the 3rd based upon my chart? Negative I. Okay, so how about 63? Is 63 divisible by 4? Which one? 64 is, which means what else is? 60. Okay, so how many is it different between 63 and 60? 62, 61, 60. So my new exponent is 3, so this guy is also I to the 3rd, or negative I. So the number of times you go backwards or go smaller is your new exponent. Does that make sense? So the difference between 60 and 63 was 3. That's my new exponent. Okay, 21. Is 21 divisible by 4? Is 20 divisible by 4? Yes, so I went backwards once, so this guy is I to the 1st, or just I. How about 42? Is 42 divisible by 4? Is 41? Is 40? Yes, so I went backwards twice. So that guy's I squared, and I squared is -1. Okay, questions on any of that before we go any further? Okay, number 3. JJ asked me, why do we need to have these, right? What is the usefulness of an I, or an imaginary number, or the square root of a negative number? Right here is its usefulness, okay? So look at number 3. It says 5y squared plus 20 equals 0. Let's try and solve this guy. So if I'm going to solve this guy, I want to get the y squared all by himself. In order to get the y squared by himself, I have to fix that 20 and the 5, right? Okay, so I'm going to subtract 20 to the other side. So I get 5y squared is equal to -20. Bless you. Okay, and then I'm going to divide by 5. So I have y squared is equal to a -4. How do I get rid of things that are squared? Take the square root, right? So roots and squares, or roots and powers, undo each other. So those old guys back in the day, and they were wearing togas and, you know, had olive branches around their heads or whatever. They're like, we need a way to solve this, because at the moment, right now, I have y squared is equal to the square root of -4. So there's no way for me to solve that. And they say, but math always has a solution, right? So that's why they came up with these imaginary numbers.
But there's no solution.
They got tired of that no solution thing. Come on, there has to be a solution, right? So when I take the square root of this guy, I get y. Now I'm the one taking the square root. So what comes out first? What does that guy become? An I, right? The negative comes out as an I. So really what I have is this I times the positive square root of 4. And what's the positive square root of 4? What else could it be? Could it be -2? Yeah, in this case it can. When you're the one that's taking the square root, you have to have the plus or the minus. Because we don't know. It doesn't tell us if it's the positive root or the negative root. So 2 times 2 gives me 4, but -2 times -2 also gives me 4. So I take the I out first, and then I take the square root, and you have to have the plus or the minus. Okay? Anytime you're the one taking the square root, you have to have the plus or the minus. Okay, questions on that? Those old guys just got tired of no solutions. Okay, now we know what their usefulness is. Now we can talk about complex numbers. Complex numbers have a real part and an imaginary part. Any number can be written as a complex number. Any number has a real part and it has an imaginary part. Sometimes that imaginary part is just 0. Okay, like the number 5. That's a complex number. Okay, so let's fill in some blanks here. A complex number is any number that can be written as A plus B times I. If B equals 0, so if that guy's not there, if B equals 0, the complex number is a real number. That's everything you've been doing so far in your whole entire life in math has been with a real number. Okay? if b doesn't equal 0, so b is something like 5 or 7 or negative 2, then the complex number is an imaginary number. And if a equals 0, so it's just like 3i, like we've been doing up here, then we call it a pure imaginary number. So, things like, this guy would be like I said, 5 plus 0i. That's a real number. 3 minus 2i. That's an imaginary number. And a pure imaginary number would be like 7i. Does that make sense? Questions on any of that? So two complex numbers are equal if both their real parts are equal and their imaginary parts are equal. That means if a plus bi equals c plus di, if and only if, when we talked about that in geometry last year, that's your biconditional, it was the double F, IFF. If a equals c and b equals d. Meaning we could go the other way. If a equals c and b equals d, then a plus bi equals c plus di. Okay, so look at number 4. Number 4 says find the values of x and y that make the equation true. Every complex number has a real part and an imaginary part. The nice thing is it tells us which ones are the imaginary parts, because the imaginary parts always have an I with them. The real parts don't. So, 2x and negative 14 are the real parts. Okay, so 2x is equal to negative 14. So what does x have to be? Negative 7, right? That's the real part. The imaginary part, like I said, the i's tell us the imaginary part. So y, if you want to put the I with it, you can, is equal to negative 3i. So yi is equal to 3i. So what does y have to be in this case? Negative 3. So the i's tell us which the imaginary parts are. The real parts don't have an I with them. Questions so far? Okay, to add or subtract complex numbers, combine their real parts and combine their imaginary parts. Essentially, you're combining like terms. So, 3 plus 5i plus 2 minus 4i. We're going to combine their real parts. 3 plus 2. 5i minus 4i. Well, 3 plus 2 is 5. 5i minus 4i is 1i. So 5 plus 1i. You can drop the parentheses if you want, so we could have done just 3 plus 2 and 5 minus 4i. That's okay. But be careful when you subtract. Just like when we were subtracting polynomials, you have to distribute the negative because you're subtracting a 3 and a negative 7i. So this guy is 4 minus 6i minus 3 plus 7i. So 4 minus 3 is 1. Negative 6i plus 7i gives me a positive 1i. Or you could just say I, you don't need the 1 in front of it. Okay, questions on that? We're so close to being done. The cool thing about i's is they behave like variables once you get them down to having only one exponent. So when you turn the page, it says use the FOIL method to multiply complex numbers. So like I said, they behave just like variables.
I know.
Because you're a smarty party pants. So here we go. First ones. 1 times 3 is 3. 1 times minus 6i is minus 6i. 4i times 3 is 12i. And 4i times a negative 6i gives me a negative 24i squared. It's positive 24, right? So we know I squared is negative 1. So what I'm going to do is I'm just going to multiply this guy by, he becomes negative 24 times a negative 1. Or essentially, positive 24. So if you want, you can cross off the I squared and just flip the sign if you want. Okay, what about the negative 6i and the 12i? What's that guy become? Negative 6 plus 12 is 6. So I have 3 plus 6i plus 24. Guess what? We can combine the 6 and the 20. I said that wrong. The 3 and the 24. So this guy ends up being 27 plus 6i. Usually we write the I part at the end, but it doesn't matter. You could have said 6i plus 27 and I wouldn't have cared. Okay, questions so far? I like imaginary numbers. I think they're cool. Just like when we had radicals and fraction exponents, we can't leave i's in our denominator. So we're going to have to do conjugates again. So complex conjugates, remember conjugates are the exact same thing, but the sign in the middle is flipped. So a plus bi and a minus bi can be used to simplify the quotient, or the division problem, if you will. Make sure I spelled that right. Yep. Of two complex numbers. When you multiply them, the product is always a real number. Just like when we multiplied conjugates that had radicals in them, we got a number, right? When we multiply conjugates that have an imaginary number in them, we'll get a number. So, look at number 7 there. It says simplify 5i divided by 3 plus 2i. Again, I'm going to show you what happens normally. Don't write this down. This is not correct. But I want to show you why it doesn't work. Okay, so if I were going to try to get this guy out of the denominator, oh, hey, you can see that. What if I just multiplied the denominator by I? Okay, watch what happens. I would get, in the denominator, I would just get 3i plus 2i squared, and we decided that anytime it was I squared, you could just cross it out and flip its sign. Well, did I fix anything? No, I just moved the I to the other side. Just like with radicals, right? If I just multiplied by one thing, I just move it back and forth. So what I have to do is multiply by the conjugate. So what's the conjugate of my denominator? 3 minus 2i. And whatever you do to the denominator, you have to do to the numerator. All right, so now I'm going to distribute my 5i. 5i times 3 is 15i. 5i times a negative 2i gives me negative 10i squared. We'll fix him here in just a minute. Remember, when you multiply conjugates, the middle term drops out. Can I stop showing that part? Do you want me to FOIL it so you can see it?
Yeah.
Okay. 3 times 3 is 9. 3 times negative 2i is minus 6i. If you're to the point where you know it's a conjugate and you can just first and last it, I'm good with that. 2i times 3 gives me a positive 6i. Perfect, we got one that's positive and negative, that's what we wanted. Positive 2i times a negative 2i gives me negative 4i squared. Okay, let's fix some things. Those guys cancel. I squared we decided was negative 1, so I'm going to cross off the I squared and change the sign to a plus. Cross off the I squared, change the sign to a plus. So I have 15i plus 10 divided by 9 plus 4 now. And proper mathematical technique says I put the real part first. It doesn't matter. If you leave that 15i first, I don't care. 9 plus 4 is 13. Okay, questions? Okay, number 8, last one. When you only have one term in the denominator, you don't necessarily have a conjugate. Conjugates are two-termed things. Okay? I could multiply everything by 5i, but then I'm just making everything bigger. So I don't necessarily have to rationalize by 5i. Could I just give him an I and it would go away? Yeah, because I squared is negative 1. So when you have one term in the denominator, you just have to rationalize by I. And then I'm going to distribute. So I get 4i minus I squared divided by 5i squared. fix our I squareds because I can't leave an I squared in my answer.
Wait, what did I? Oh, yeah.
You good?
Yeah.
Okay. So essentially I have 4I plus 1 all divided by a negative 5. Or, if you like it better, 1 plus 4I all over negative 5. And I'm okay with your negative being in your denominator too. I'm sure there's some cranky math people in the world that tell you you can't have negatives in your denominator and you have to write it in the right order and make sure you use a ruler when you graph. Man, I'm just not cranky like that.
That was definitely in my 8%.
Yeah. Okay, questions on imaginary numbers? Okay, what I would suggest is that you, on the top of your worksheet, write the powers of I. So I is I squared is negative 1, I cubed is negative I, and I to the 4th is 1. That's my big suggestion for the day. But let's look at your worksheet. So, at the top, 1 through 6, it looks like it sort of broke it down a little bit for you. 1 through 6, make sure you take the I's out first. Okay, and then you're doing straight radical stuff that you've done before. 7 through 11, you're fixing those I squares. I cubes, I to the 42nds, all those things. 12, 13, 14, 15, 16, you're adding and combining like terms and subtracting, so be careful. 17 through 20, you are multiplying, so just FOIL. 21 through 24, those are conjugates. 25 through 30, you're solving. Write yourself a little note right there. You should have a plus or a minus in your answer. So there's 2 answers. You need a plus or a minus with all of those guys. 31 through 34, those are the real parts and the imaginary parts. So you just set the real parts equal to each other, the imaginary parts equal to each other, and tell me what M and N equal. How about we skip the word problems again? Just looking at your worksheet, does anybody have one they want me to do with you? You're like, ooh, I don't know what that's asking me. Yeah, Rachel. 30, you bet. Okay, so 30, it says solve this guy. So I'm going to move the 12 to the other side. So I have 3/4 x squared equals a negative 12. Now, it's a fraction. I can't divide fractions, so I'm going to multiply by the reciprocal. So I'm going to multiply both sides by 4/3. Negative 12, I'm going to divide it by 3 first. So I get a negative 4 times it by a positive 4, and I get negative 16. Again, if you're not sure, you can use your calculator too. Oh, hey. Stop. And then take the square root because I have the a squared. So I want to undo that. So x equals, the negative comes out as an I took the square root, so I need a plus or a minus. And the square root of 16 is 4. So that guy is plus or minus. That's really hard to see. 4i. Yeah.
So then for all of those problems, are we going to do the same answer, plus or minus?
It'll be plus or minus something. So,
okay, so it's not going to be like plus 7 minus 4, something like that?
yeah. So they'll all have a plus or a minus with them. So let's do like 25, just so you can see something else too. Or maybe, yeah, let's do 25 because I got some in there. So the plus or the minus just comes from you are the one taking the square root. So if I look at 25, this guy says, okay, I have 5n squared. I'm going to move the 35 over, so negative 35. So n squared equals a negative 7. I'm the one taking the square root. So n equals, just go ahead and put the plus or minus because you took a square root. The I comes out, but do I know the square root of 7? Does he break down any further? No, so I can just leave that guy as this root 7. So every one of them will have a plus or a minus. Every one of them will also have an I with them. If you can take the square root, take it like we did over here and we got the 4. If you can't, just leave him in the radical and reduce him down as you can. Abigail.
Does it matter if one is before or after the 7?
Usually we put him outside, out front of the radical so we know that he's not under it. That's the only thing. But no. Matthew. 34, you bet. Okay, so 34 says find the values of m and n that make the equation true. All right, so I'm looking for real parts. This guy doesn't have an I and the 3 doesn't have an I. So I'm going to set 7 plus n equal to 3. So when I subtract 7, n is equal to a negative 4. So that's part of it. That's the first part. The imaginary parts are the guys with the i's. So on the second part, I'm going to say 4m minus 10. And this time, because it's a whole lot of parentheses, I'm not going to use the i's. Is equal to a negative 6. You could put the i's with it if you want, but essentially you're just dividing them out. And then I'm going to add 10. So 4m is equal to 4. Divide by 4, so m is 1. You don't have to, because they just want to know what would m and n have to be to make it a true statement. So you can just leave it n is equal to m is equal to. Yeah, good question. So, on your worksheet, you are doing 1 through 34. You don't have to do the 2 word problems at the bottom. So do 1 through 34, not the word problems, Thomas. Okay, any other questions?